Okay. So the objective of this webinar is to give you an overview of what is an antenna design for IoT devices. So the target audience is mainly project manager and people who want to know a little bit about antenna design, specifically focused on IoT, meaning that I won't speak about antenna for satellites, for instance. And also, it's not going to be a very technical presentation, but mainly I will give you an overview of what is important and give you the key point to select an adapted antenna solution for your device. So the message to deliver with this webinar is that an antenna should not be an afterthought component, meaning that you really need to take this component very seriously. We are speaking about wireless devices, so if the antenna doesn't work, the device will not work. Then antenna should not be considered as a regular component. In fact, the antenna is very sensitive to whatever is around the device and also sensitive to some other components which are part of the device. So you really need to be careful with the design and the implementation of the antenna of your device. And finally, I wrote antenna design, the earlier the better, which means that the earlier you take into consideration the antenna design, the best performance you can expect. If you start the antenna design too late in your device design or implementation, you might get some trouble to reach high radiated performance. Okay, the program of this webinar, I will start with some generalities, basically telling you why antenna design can be very tricky. Then I will go through the whole project phase of a generic connected device, and I will mainly speak about antenna design. So basically, for each phases, what you should consider regarding the antenna. Then I will explain you why the antenna can really impact on the radio link budget and therefore decrease, for instance, your coverage area for a device. Then in the section 2, I will speak about antenna sensitivity, and I will explain why an antenna is such a sensitive component compared to others and to what it is sensitive. Then in the third part, I will speak about several antenna parameters that are very important when you do the design of your device. In the section 4, I will give you some questions that you should ask yourself to make the best antenna choice for your design integration. And finally, I will conclude. Okay, so let's start with the first part. So,
sorry to interrupt you.
Yeah.
Just because we already have some questions, and I forgot to mention it in my introduction. You can ask questions about what Cyril is introducing. Anyway, we will answer your question at the end of the presentation. So we will select the most interesting and relevant questions, and we will answer them at the end of the webinar. So feel free to ask any questions regarding the topics that Cyril is addressing, and we will answer them at the end of the presentation.
Okay, thank you. Okay, let's continue. So section 1, generalities. So why an antenna is such a tricky component compared to others? That doesn't mean that other components are easy. Anyway, so the first point is that the antenna design complexity is constant regardless the device complexity. What I mean is that you can have a very simple device, such as, for instance, a simple button, that will require a very complex antenna design. On the contrary, you can have a fairly complex device that will require a very simple antenna implementation and design. So this is very important to make the difference between the device complexity and the antenna device complexity. Second point is each new device requires a specific antenna development. Actually, you will always need to adapt your antenna to the device architecture and design. It's very difficult to find an antenna that will work the first time without doing anything when you implement it in your device. Sorry. This is mainly true for integral antenna. In some cases, you can have some external antennas that are much easier to implement. Also, you need to adapt the antenna to the device environment or the use cases. For instance, if you know that an antenna or a device will be placed against a wall or held by a user, you really need to take that into consideration when you design your antenna or you adapt it to your device. And the last point is that actually antennas are quite difficult to evaluate, or at least the radiated performance of a device, they are quite difficult to evaluate. To measure them first, you really need some expensive facilities such as anechoic chambers. You have a picture here. So it's not given to everyone to go every day to an anechoic chamber just to do a test. Then even if you have antenna measurements of your device, it will be difficult to evaluate the real life performances. As I said, since the environment might be different from one use case to another, you may have some varying performance of the antenna. Okay, now in this slide I will go through the different project phases of a connected device design and mainly focusing, of course, on antenna design. So let's start with the requirement and specification phase. In this phase, regarding the antenna, you should define basically all the protocols and bands you want to cover. That will define the bandwidth you need for the antenna and so on. Then you may want also to already set the target in terms of radiated performance. So I don't know, for instance in SIGFOX we have different classes for devices. For instance, class 0 is the best with a very high radiated performance. Then you have the class 1 that is a little bit lower and so on. So that's the right moment to set in which class you want to be, for instance. Then you also want to select all the certification you need to pass. Let's take an example. If we design an object that will be used in the US, then you need to pass the FCC. So this is something you need to take into account from the beginning. And then, as I said, you also need to define the different use cases that will basically give you more or less the environment of the device. And also, it is the right moment to select the product dimensions that will help you to select the right antenna topology. Okay, now let's move on to the hardware concepting phase. So in this phase, this is where basically you start the development of the device, but everything is still open. So for instance, you are defining the casing of the device, which will have an impact on the antenna. We'll come back later on that point. Then the antenna volume and location should be selected at this moment of the project, so that the antenna designer can already select maybe a few antenna topologies that might work, or even select the right one already. Then it is interesting also to select manufacturing technology in the case if you select, if you want to build a specific antenna for your design, for your device. This is important because this will basically give you the level of freedom you will have on your antenna design. So manufacturing technology should be selected quite early in the device design. And then it's also nice at this point to already have a rough idea of the PCB floor plan with all the main components placed, because they will maybe have an impact on the antenna performances. Okay, at this point you may have to come back and change a few requirements, so this is not completely straightforward, but after the hardware concepting phase, usually you have the hardware development, and in this phase you do the antenna design. You may need to have an antenna matching circuitry, so this is the moment to place it. Then you need to also find a way to interconnect your antenna with the rest of the device and with the RF module, for instance. So this is not an easy part, as an antenna is an electromechanical components. You have really to connect it to the PCB, and this is usually quite difficult. And then this is the moment where also you detail the PCB routing and the placement of all the components, and that allows you to really tune the selected antenna topology. Then when the hardware development is done, you move on to the hardware validation phase. In this phase, this is when you have the prototype. So this is where you are going to finalize the antenna tuning. So you might need a few runs of prototypes. It might not work the first time, but then you try to converge to a final antenna tuning. Then you have to evaluate the radiated performance of the device, and also if everything is working fine, you do the certifications. If something is not working perfectly, you might come back to the hardware development phase, but otherwise you go to the production phase, and in that phase you have to make sure that the manufacturing process, so for the antenna, is well controlled and is fine, and then also to make sure that the assembly stability of your device is functioning well. Okay, now I'm going to talk a little bit about the antenna impact on the radio link budget. So this is a very important slide, because this is where I'm going to explain you why it is so important to really make a good antenna design for your device, and what you can lose if your antenna is not good enough. So first, what is the link budget? So the link budget is a number that is calculated, and that would help us, SIGFOX, to define the network coverage area. The base stations are placed according to this link budget, so this is quite important. The network is dimensioned with this number. So the link budget is basically, to make it simple, the device radiated power minus the base station radiated sensitivity. So if we look at the picture at the bottom of this slide, we have on the left hand side a device with a transceiver and an antenna, which transmit a certain amount of radiated power. Then we have the propagation, in which we know that we are going to lose some energy. And on the right hand side we have the base station. The base station has a certain radiated sensitivity, which is fixed for, this is like the network, so this part is fixed. And between the two, the transceiver and the base station, we have a link budget for SIGFOX that is about 160 dB. So this is a lot. And that means that if we don't have any perturbation, the theoretical range between a device and a base station can be about 2,500 kilometers. So we can have a distance between the object and the base station that is quite huge. But in reality, we know that the path loss might be impacted by trees or buildings that will decrease basically this link budget, this distance or this range. In our case, we don't place base stations every 2,500 kilometers. For instance, they are usually placed maybe 50 kilometers away from each other. In the cities, of course, they are much closer, but if they are placed 50 kilometers from each other, we have a margin of 35 dB, which is quite good. and will allow a few trees and buildings between a device and the base station. Actually, a lot of trees and buildings, no problem. But also allows some indoor and tough environment applications, such as, for instance, buried device. If we look at this, the picture, we see that the device transceiver, so the RF module, will provide you a certain amount of power that is fixed. Then the propagation, the path loss, is the same for everyone, and the base station performance is optimized. So the only parameters that can reduce this link budget and therefore the range or the coverage for a device is actually the antenna the antenna of the device. So this is why it is very important to succeed in the antenna design for a device. Just to let you know, when we add 6 dB to this link budget, we multiply the range by 2. So this is just a number to remember that is quite important. Okay, now we are going to move on to the next section where I'm going to talk about antenna sensitivity. So let's start with the best part, a little bit of antenna theory. So this is going to be very light, but it's necessary to understand what is following. So first, what is actually an antenna? So obviously an antenna is the component that will convert the conducted RF signal into a radiated electromagnetic wave. So when we speak about physics, an antenna is a metallic structure in which an alternating current is flowing, and this current will generate some electric and magnetic field around the antenna. If this current is strong enough, it will generate strong E field and electric and magnetic field. And if the antenna is well designed, those fields, they will manage to escape from the near field area, which is very close to the antenna, to the far field to become really radiated electromagnetic waves. The antenna needs to be dimensioned to maximize this radiation, and the dimension of the antenna will depend on the antenna type. For instance, on the right-hand side, we have a simple dipole with the feed point at the middle, and a dipole is usually half a wavelength at the resonant frequency. Okay, now two very important parameters for IoT devices. When we speak about antennas, we can find a lot of parameters, but in the case of IoT devices, what really we want to optimize is the impedance of the antenna and its efficiency. Why we talk about impedance? If we look at the bottom right of this slide, we have a small scheme which explains what is the antenna impedance and mainly the return loss criteria. So at the antenna interface, we have some RF power coming from the RF module, and so this incident power will be partly reflected and partly accepted by the antenna. And then what is accepted by the antenna will be radiated. The return loss is the ratio between the reflected power and the incident power, and this parameter defines the bandwidth of the antenna. So, which means that first the energy coming from the RF module needs to go inside the antenna, and then it can be radiated. The efficiency is basically the ratio between the power radiated by the antenna over the incident power. So these parameters are really the two essential parameters that you need to really understand for IoT devices. Then you have other parameters such as gain, etc. But they are, I would say, less important. So if you need to remember two parameters, they are the two. Then also one thing that is interesting is that an antenna is a reciprocal device or component. meaning that it has the same properties when used in RX or TX mode. Okay, now I was talking about the Nearfield and the Farfield region. So you have to understand that around an antenna, you have these two areas that are defined. In the near-field area, this is where the fields, they are completely linked to the current repartition or the surface current of the antenna. In the far-field area, the fields, they are not directly related to this current anymore, and that means something very important. That means that if you place something in the near-field area of an antenna, you will basically impact the antenna properties. Whereas if you place something in the far-field area, you will only impact on the propagation and not on the antenna properties, and for instance on the radiation properties of this antenna. So this is important to really understand that you have the near-field area, which is close to the antenna. In the case of SIGFOX device or generic SIGFOX, it's about a few tenths of centimeters, and that includes, for instance, the casing that will have an impact. If someone is holding the device, then the hand will be in this near-field area. The far-field area, well, it's more about propagation, as I said, so the tree, which will be between the device and the base station, will only impact on the propagation. Okay, so now we will go through a few examples to show you how much sensitive an antenna is. The parameters we will look at is the return loss. We can see in the top right picture, we have the simple dipole, and then with a vectorial network analyzer, we can look at the return loss directly. So where we have the marker, the small bluish point, this is the resonant frequency. And let's see what happens when we put a metal plate next to the antenna. What we can see is that, well, this resonance is moving. So this is true. The antenna is actually impacted by the metal plate, and the detuning is actually quite huge, as you can see in the small video. So basically that means that a simple dipole cannot be placed against the metal plate, or at least if you do so, you cannot expect to have the same performances than if it would be in a standalone condition. And now let's look at what happens when we hold this dipole. What we see is basically the same behavior, so a huge detuning of the antenna, and you don't actually need really to touch the dipole or the antenna. You need just to be close enough to detune it or to impact on the antenna performances. Now let's take a third example, a small wooden board, and you will see that you also have an impact from a wooden board. So of course, when we look at this video, we see that the impact is not as huge, for instance, as for a metal plate, but still you have a slight detuning. Just to understand, in that case, we have a dipole that has a fairly wide bandwidth. So in that case, this is not really a problem. We still have a good return loss, and the antenna should be working next to a piece of wood. But if we have a very narrow band antenna, it might really be a problem. Okay, so these three examples just was to show you how much sensitive an antenna is to its nearby environment. And you could see that, well, a metal plate or a hand user will have a large impact, and even a wooden board will have some impact. And what we have seen is the impact mainly on the tuning of the antenna, so on its central frequency. But you have to understand that it also have an impact on the radiation pattern. So you will have radiation properties modified, but also on the efficiency of the antenna. For instance, when someone is holding an antenna or a device and put his hand very close to the antenna, a part of the radiation will be absorbed by the hand and therefore not radiated. Now, in this slide, I will show you to what an antenna is sensitive within the device, meaning that the antenna is sensitive to the way it is implemented in a device design. So for that, we will go through again a few examples. So the first one, usually we have an antenna component, and we think, okay, so this is the antenna, this is the part that is radiating. But in fact, in the case of small devices with small antennas, this is not only the antenna that is radiating, but it is the whole device. So basically the antenna element plus the rest of the device. And you can see in the bottom right animation that some RF currents are actually flowing through the whole device. In that case, we have on the top a small monopole antenna mounted on a PCB. And you can see some current flowing through the whole PCB. Also, if we have some currents flowing through the whole PCB, that means that if we reduce the size of the PCB, it may have an impact on the antenna. And if we look at the bottom left, we have two examples of smaller integration. One with an antenna and a large PCB, and the other one with exactly the same antenna, so there is absolutely no modification, and the smaller PCB. And what we can see is that between the two solutions, one will have a perfect efficiency, so 0 dB means 100%, while the other one will be a little bit lower. So we lose some percent of efficiency, but not only. We can see also that we lose in terms of bandwidth. We can see that the frequencies in which we have a good efficiency are much less wide. So, we have basically a reduction in terms of bandwidth and efficiency. Now let's look at the device casing. We have here an example of, this is a typical SIGFOX device. So this is the Sensit. And I have simulated the antenna impedance, so the return loss again, with and without the casing. So this is a simple plastic casing with, I think it's PC, ABS plastic. And we can see a detuning of 50 megahertz between the with casing configuration and the without casing configuration. So here you can see an example that really illustrates that the casing really have an impact on the antenna tuning. It may not have any impact on the performance of the antenna, but this example shows you that you really need to tune the antenna in its final configuration with the casing and actually with the right casing. Nowadays it's easy to build with a 3D printer a prototype, but this is not enough for the final tuning. Other components such as battery, wires, and displays, or huge components usually, they will also have an impact on mainly on the tuning of the antenna. Just if we speak quickly about an off-the-shelf antenna, basically, as we have seen, it will be impacted by the rest of the device, so the location is critical. A retuning of this solution will be necessary if you select an off-the-shelf antenna. And yes, following a datasheet might not be actually enough. So you have to be very careful when you read a datasheet, an antenna datasheet, because it is written for one configuration, one platform. So you really need to be careful and to make sure that you understand perfectly this datasheet. If you have any doubt, I think the best is to contact directly the suppliers and they will give you some advices. Until this part, I think the main message of this webinar was one device, one antenna. You really need to adapt each antenna to your device, your specific device. Okay, now let's continue with the third section where I'm going to go through a few antenna parameters that are important for an IoT device design. So the first parameter that is important is the volume you allocate to the antenna. You have to know that the product efficiency time bandwidth will actually limit the antenna efficiency. The antenna volume limits the product efficiency time bandwidth. So if you don't allocate enough volume for your antenna, then you will have a reduction in terms of efficiency or bandwidth, and even maybe on both parameters. And also, the smaller the volume you allocate to your antenna design is, the more difficult it's going to be to do the antenna implementation. So if there is no need to reduce the volume of the antenna, don't do it. I mean, it will just reduce the radiated performance of your device and make the antenna design very difficult. Now, the antenna location is also very important. Depending on the antenna topology, you cannot place it anywhere you want. We have on-ground solution, for instance, patch antennas, which can be placed over the ground plane of your device or over your PCB, while you have what I call off-ground antennas, like in the picture, which are placed on the side of the PCB or the ground plane. In that part we have, for instance, monopole antennas. So depending on the type of antenna, you cannot place it wherever you want. Now, the other components nearby the antenna, they will have actually a huge impact on the antenna performance and tuning. For instance, if we have a huge battery right next to the antenna, it will somehow load the antenna and detune it. So it might not be a problem, but you need to take that into consideration when tuning the antenna and when basically designing it. And then some components with lossy materials may reduce also the efficiency of your antenna. If we have too much metal part right next to the antenna, this might also reduce the bandwidth of the antenna. And finally, if we have wires right next to the antenna, or even some complex structures, they can maybe generate some unwanted resonances that will have impact on the radiated performance again. And on top of that, those unwanted resonances, you will not be able to control them. So they will be wherever they want in the spectrum, and usually if you have one, it will be exactly at the SIGFOX frequency. So you don't want those kind of resonances. So be careful when you have wires everywhere. You just need to make sure that they will not impact on the antenna. The last parameter that is very important is actually the casing. As I said, it will have an impact on the tuning of the antenna. But if you select a casing with a lossy material with high dielectric losses, you may have some decrease of the antenna efficiency and therefore to the radiated performance of your device. Also, having a metal casing can be very nice, but that also increases the design complexity for the antenna. And of course, avoid full metal casing. So the conclusion of this section is that basically an antenna is sensitive to almost everything. And again, one specific integration or at least tuning for each device depending on all those parameters. Now the last section, which is called what are the right questions to ask yourself to select the best antenna solution. Here are the questions. So the first one is, do you need an internal or an external antenna? Integral antennas, of course, you can, if you want to build a very nice device, they are the right solution. But if you really want to have a best-in-class radiated performance, it might not be the best idea. Especially if you don't want to invest too much on the antenna design, then an external solution could be a good solution. If you want to have an internal or an integral antenna, then just make sure to really invest on the antenna design, because this is going to be tricky. So basically, external antenna are easy, integral antennas are more complex, and especially if you have a very small device with a high level of integration, this is difficult. So talking about the level of integration, so what it is, if we have a small device, so of course the level of integration is quite big, but if we have a large device with a lot of things inside and a very small volume dedicated to the antenna, then this is also what I call a high level of integration. So the size of the device will be important, but also again the volume you dedicate to the antenna. So basically, again, the more volume, the better, the easier. Again, about this level of integration, you need really to select the best location for the antenna inside your device. And again, the other components nearby the antenna. Now the target performances. So in SIGFOX we have defined device classes. So as you can see in these tables, the first one is for the zones where we want to transmit 14 dBm, and the other one is for the ones where we transmit 22 dBm. So for instance, the first one is HC zone, and the second one could be FCC zone. So the target applications might drive the target performance you want to achieve. In fact, if you are in a very complex and tough environment, you need to go for the class 0. So you really need to achieve this class to use the networks, the SIGFOX networks, at its maximum capacity. On the other hand, if you have only an outdoor situation, then and you really want to have an integrated device, a very small device, it might be interesting to relax a little bit the target performance and still enjoy the SIGFOX network. Of course, you don't want to go too low in terms of performance, but you need to find the right trade-off between performances, antenna volume, and integration level. If you really want to have a high-performance antenna in a small volume with a high level of integration, you need to understand that you will need to invest a lot in terms of antenna design, and this will also take some time to find the right solution. And sometimes this is not possible. So you have some limitation physics, and that's it. But let's say for SIGFOX we have a really narrow bandwidth, so usually you can find a solution, but just it can be difficult and therefore takes some time and investment. Now the R&D investment capability. So you need to ask yourself, okay, I want to do a specific antenna design for a very specific device. Well, can I do it? Because to do antenna design you need a lot of things. First, you need, to know about antenna design, of course, or to have someone who knows. But also, you need to have the right equipment to make these antenna measurements. You need some very expensive equipment, such as anechoic chambers and vectorial network analyzer. Also, if you want to do a specific antenna design, as I said, you need to take into consideration the development time that might take some weeks or even some months in some cases. And also, you may need several prototypes, iterations to reach the final design. Another question you should really ask yourself is, what is the environment of the end device, and basically what are the use cases? If you know that it's going to be held or worn by someone, if it's going to be placed against a wall or on a car, a truck, etc., you really need to define all the use cases in which you really want the device to work. Of course, you can have some other use cases where it's less important, but really it's important to define which are the most important and to write like a priority list and give it to the antenna designer so that he will be able to select the right topology and solution. And finally, the production volume, it is actually quite important because so when you do a specific antenna design, you will need to produce the antenna, and therefore you will need to access to some technology. For instance, here we have two different antenna technologies, manufacturing technologies. The first one is a quite complex one. It's called LDS, laser direct structuring. This is basically some kind of printing, metal printing on a plastic surface, to make it simple. And this is only available for really mass production, so you need to be over hundreds of thousands of pieces. So if you only want to do like, I don't know, 10,000 devices, this is not the right technology. On the other hand, you have, for instance, at the bottom of this slide, a metal wire antenna that is much easier to reach for small volumes, but it is also less less optimized. So with the first one, you have well, let's say you can do the best antenna solution. You can really design everything you want. You have a lot of freedom in your design. Whereas in the second one, it's much more limited in terms of design. So you won't be able to achieve the same performance with the second one than with the LDS solution. But to use this first solution, you need really to have a huge volume. Also, the target price is important to set as soon as possible, and the assembly complexity is also something to take into account. Okay, now I will conclude. So, well, I think I gave you the message that, well, the first point, the full device is part of the antenna. So the antenna is not only the component called antenna in an IoT device. For most integrated antennas, the whole device will be actually part of the antenna. The second point is the earlier the better. So the earlier you start, at least to consider the antenna design, the best performance you can expect. If you start too late, then it might be very difficult to achieve acceptable performances. The third point is that antenna properties will vary depending on the environment and the device itself. And again, basically everything can impact the antenna. And to summarize, yeah, antennas are not standard components. You really need to differentiate, for instance, I don't know, resistor and an antenna. This, well, this is obvious, of course, but really antennas are different, not standard components. And finally, just in this conclusion, as Johan said, a white paper is available on sigfox.com. So it is a little bit more complex. You have some other things in this white paper, so just have a look at it. So thank you.